So we have our pink sheet, which is our outline here, and the polymerization of Roman numeral 6. I see use of appropriate catalysts, so let's make sure we mention that. So here's the same exact reaction that we did. Here's where we made polypropylene. What catalyst do we need to use? Well, it's an H plus catalyst, okay? And what would be an exact? You can't go to the stockroom and just say, give me some H plus. You're going to have to give some more information. What catalyst would you use here or suggest? What's your favorite H plus source? Glad? What's your favorite strong acid source? Hydrochloric, okay? Would you want to use HCl for this reaction? Would you want to use HCl as a catalyst? Why not?
HCl also attached to it.
Because if you use HCl, you're probably going to get that there. Addition of HCl to the alkene, standard simple reaction. We want the H plus to be attacked, yeah? And we want to get the carbocation, but what do we want to attack the carbocation if we want polymerization? We want another alkene to attack. You don't want the chlorine to attack, because if it does, you're just going to get that. You won't get polymerization. Okay? You want to use an acid that does not have a nucleophilic anion associated with it. Your HX is like HCl, HBr, HI. The halide is nucleophilic and it will add. What acids will not add?
Sulfuric acid.
Sulfuric. These were stated earlier when we did the hydration. Sulfuric, phosphoric, and what's the other one? HF. Okay? Those acids, the anion will not ever do anything. So if we use like sulfuric and the anion was HSO4 minus, what I'm telling you is this guy will not add. And so the only thing that can add is what you want to add. And so this can come in here and then off you go. Boom. You keep going and it adds over and over and over. So you have a non-nucleophilic anion. That's the type of acid you want to use. Any questions about this polymerization? Think mechanistically, ability to show a repeating unit. This reaction started by reacting with a H plus cation. We just call this cationic polymerization because it was initiated by a cation. What if the polymerization was initiated by the anion? What might you want to call it? Anionic polymerization. What if it was initiated by a radical reaction? Radical polymerization. This is an example of a cationic polymerization because it's initiated by a cation, which was the H plus catalyst. CAT does not stand for cation, that stands for catalyst. But H plus is also a cation, right? Okay, that was polymerization. Alkenes reacting with cations. Let's go back over here because this was an example of a ring expansion. Let's see how we did on this mechanism. Mechanism means using appropriate arrows, show all electron movement, go from here to there. Every intermediate needs to be a correct Lewis structure, with correct charges, of course, etc. How does this happen? That's what we're showing by mechanism. We have H plus in water, right? That's what that means, yeah? The only reaction we know thus far of an alkene is reacting with H plus. Think about it, that's all we've done so far. So you got an alkene and you got an H plus. That's the first step, yeah? Question though, we're going with the cation at top or bottom. Huh. Does it look like it would be selective? Is the cation top or bottom on this alkene? Either way, it would be secondary. So there's really no selectivity there. So do we just do either or both? Well, we got to sort of see what's going on. Maybe we got to consider some other things here. Ultimately, let's back up over here. I don't like to look too forward in our mechanism because we want to take one step at a time, but can everybody agree that maybe we want this cation? If we could form that carbocation, could you get home from there? Yeah, because then that looks like water adding here, and then you lose proton, you got product. In fact, let's just go ahead and finish this up, right? H2O, these electrons make bond to cation, and what does that do? Boom. Boom, boom, boom. Oxygen, 2 H's. One lone pair left, and lo and behold, that's a positive charge. Now, how do we get home? Something has to take the H. What's the minus here? There's got to be a minus. It's shown very generically. Got to be a minus. You could throw one up there. I mean, what is this? Water and ACl? Well, maybe not. But we'd have the problem. Maybe we would get a chlorine product. Water and sulfuric. Then you got an HSO4 minus to go with this. Or we can use what to remove the H? Or we can use water, take the H, leave the electrons behind, and we get that product plus what?
H3O.
H3O plus, which is essentially acid reform. The acid is the catalyst. It's reformed over there. It's now sitting with the water again. So that would take us home. The question is, how can we get from here to here? Cation on a carbon with 2 methyls. There's a carbon with 2 methyls. Somehow we want a cation there, maybe? Well, I'm thinking if we want a cation there, let's form the initial cation up top, so then we can rearrange it to there. Let's see how that goes. See if we can get there. One step at a time. Maybe that doesn't get us there, but let's explore it. So I'm going to attack. I'm going to pull this down. Okay, here's the pi bond. I'm pulling it down. The bottom carbon is going to bond to the H, leaving the top carbon as what? Leaving the top carbon as the cation, the bottom carbon bonded to H. Boom, bond to H, top carbon cation. Nothing new. Alkene reacting with H+. What can we do next?
Can we take break the bond opposite the plus?
This is a 7-member ring. That's a 6.
Can we take the one on the opposite?
We have a secondary carbocation. We know cations like to do what? Rearrange. We could shift a methyl over. If we move the methyl over, well, then we would no longer have a carbon with 2 methyls. But we got to have that, so that doesn't make sense. Also, moving a methyl over would not do anything to the ring size. But look at this. What if instead we disconnect this bond? Now, it looks like it can never do this. What if we disconnected this bond and moved it and bonded it there? Now, the way I have this drawn, it looks like, how can this bond here? But really, these things can maybe, you got these wide bond angles. It breaks away and it bonds here. Let's break these electrons away from here and bond them here. I'm going to redraw this just like this, but then I'll rebond it. Boom, boom, boom. UH. Okay, what did we do? Took these electrons, there's the atom, and instead of these electrons binding to there, I binded them to there. Now, what should we show now on this carbon here that lost the bond? Plus charge on that carbon. That's connected over there. Now what is that? What size ring is that now? 1, 2, 3, 4, 5, 6-membered ring. What is this? That's actually the same, that's that. It's just drawn nicer over there. All this is the bond disconnected from up here and went down there. And when it did that, it became a 6-membered ring. Coming off of the 6-membered ring is a carbocation with 2 methyls. Carbocation, 2 methyls. The new H is where? Well, next to that group. The new H is still here. Really what happened is this bond used to be bonded there, but instead it shifted. Now it's bonded there. It's an alkyl shift. Basically, this carbon shifted instead of bonding there, it's now bonding here. This is the alkyl group, but it's a ring contraction, ultimately. Now we have this, and now we're home free. So this is a carbocation rearrangement. Why would it do that? It went from secondary to what?
Tertiary.
Now tertiary. But what's another reason it did this? It went from 7 to 6. 6 is a better sized ring because the 7 actually the bond angles are too wide. 5 and 6 are your best rings. From there we can get how many total intermediates on the board? Total intermediates. 3. Original cation, rearranged cation, because this is the same thing, right? We got this species where it's the final product just protated, but that's an actual intermediate. Until we lose the H, do we not get the final neutral product? 3 intermediates, what's the rate determining step most likely? Typically forming the carbocation, because from there we start going downhill. This is more stable, right? And this is actually more stable because the reason here is everything has an octet. Carbon doesn't have an octet here. Here everything has an octet, including the oxygen. So once you get here, you start falling downhill. You fall downhill even more, and then you fall downhill to your neutral product. And as you fall downhill, it doesn't take much activation energy. Greatest activation energy is going to come from making your original carbocation. How do we do on that one? Questions about that one? So that's a ring contraction. How about this THC mechanism? How do we do on this one? Anybody get this? Feel confident in your mechanism? It's actually fairly straightforward. It's really only 1, 2, it's only 3 steps, right? Any questions about this mechanism? Question?
I guess I'm not sure if I got it out of the way. I was confused after I was confused where the methyl shifts over, I guess.
There's no methyl shift.
I didn't see how you got two methyl groups on the carbon beside the oxygen.
Well, you already have two methyl groups on the carbon. The methyl groups are already there. Carbocation, I think the first structure, it already has two methyls. Do you see the two methyls?
Yeah, I see it now.
Perhaps that's why I like to, if I have something like this, boom, 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 sometimes I'll draw in. These are methyls on the end, right? Are there other questions about that one? Next on the pink sheet. It's a new letter. A were electrophilic additions involving a carbocation intermediate. B is going to be reactions without a carbocation intermediate. And if we look at the summary page on the previous pink page, we've looked at all these reactions up here. Okay? They all involve reacting with H plus and a nucleophile, either like halide, water, or alcohol. And then we also have like the polymerization up here. They all involve, everything we've done so far starts with reacting with H plus. Down here we're going to introduce other reagents. Okay? There's going to be a thus more complex nature to things. These do not involve a carbocation intermediate. Do not. The first reaction we're going to look at is reacting an alkene with X2, like Cl2 or Br2, elemental halogens. We're going to add a halogen to each carbon of the alkene. We're going to add the halogen across the pi bond, the terminology is called. Okay, we'll start there, and I think we'll go around sort of clockwise here. And so on the white sheet, it starts right here. And next week in lab, we will be doing a bromination of an alkene. When we say bromination, it doesn't mean hydrobromination. It's just bromination. And that implies that it's Br2. And thus next week we'll be back on schedule for lab, okay, which is bromination of transtylbene. Okay, so let's look at this. It's actually known to be an anti or trans addition of the halogen to the alkene. Typically, you only use chlorine or bromine here. Iodine actually just does not work. If you did some thermodynamic calculations, you would see that iodine would be an endothermic reaction, and it's just not favored. Fluorine, on the other hand, F2 is too reactive. It's certainly exothermic and thus favored. The problem is it's so exothermic that it's dangerous and explosive. Typically. So usually just chlorine bromine here. All right. In terms of predicting the product, and if you don't include stereochemistry, this is the easiest reaction you'll ever see. We just add a chlorine to each carbon of the pi bond. Chlorine over here, chlorine over there. Okay? And we'll learn when bond angles need to be important. I could have drawn this chlorine down. Of course, you've got free rotation. It doesn't matter. Chlorine on each carbon. The more detailed thing will be what's the exact mechanism and also stereochemistry involved here. Because as we move forward with these reactions, we'll start talking about the stereochemistry. Okay, reaction. Well, what's our electrophile? That is, what does the pi bond attack? We don't have H plus or even a polarized HCl. Okay, if you have polarized, you know you got dipole, that's partial plus, and the electrons attack partial plus. Chlorine, is that a polar molecule? Cl2. It's formally not a polar molecule. But the halogens are sort of schizophrenic. And they pull on each other, and they're known to be polarizable. That is, at any particular second, one may be minus and one may be plus. Now, it's not formally polarized, but we can polarize it, okay? And you just have to sort of go with that. You can look up polarization of halogens and talk about it, probably some physics of charge separation. It's kind of a temporary polarization. Halogens are known to do. Okay, thus we can say one is partial plus. Now, but it's not ionic. Never show chlorine as Cl plus, Cl minus. Chlorine is not ionic. So we have to use it like this. But now the pi electrons can be attracted to that one, and we can make bond to it, and when we make bond, we have to kick the other one off. So it's sort of making bond and the other one leaving at the same time. Sort of like a leaving group. And we'll say that many times going forward. In the end, you have to look at the mechanisms, make sure you understand. You have to test your knowledge. Hey, do I understand what's going on here? Okay? I just gave you my 5-second overview of it. Your textbook will give you the same thing. Important question. When we attack here, where are we going to leave cation, left or right? Was it the same as before? On the left, right? Correct? Yes. So here we go. Here's pi bond. We're going to break away over here because we're going to leave cation and go attack the chlorine and make bond to chlorine. Now when we attack the chlorine, this chlorine has to get kicked off. So these electrons move on to that chlorine, and what does that mean to you? The bond is being breaking, the electrons move on to chlorine as the 4th lone pair, and so that generates chloride. So attack chlorine, chloride generated, bond to chlorine, but where did we leave cation? The sites that we should leave it. Okay, here's the problem though. I thought we were under B, and what does B say? These are additions without a carbocation intermediate. What is that? It's a carbocation intermediate, so what gives? Well, guess what? This is not actually formed. Why? Well, this is it. Here's the story. First off, we could get this product by simply having the chloride that's formed, then add here A. That would give that product. Hopefully you see that. Problem is that's not the mechanism. We'll say why going forward. Because look, which chlorine is going to be able to bond to this cation fastest? This one, which is not connected, or this one, which is now bonded? The answer is this one. This is going to bond faster because it's sitting right there. For example, let's do a high five. Who's going to be able to high five me faster? Her or me? Okay, let's go. Sorry, I won. Why did I win? Because my other hand's sitting right here. Boom. Okay? You're not going to beat me. This chlorine is actually a long ways away. It drifted away. This one is closer. These electrons are going to be attracted to that plus faster than the other one. So B is actually what happens. These electrons come in. I call that back bonding. Your textbook may not call it back bonding. That's going to be faster. And when these electrons come in, what do you get? Well, just what this arrow shows. These electrons bond here. It's nothing fancy. Then show it bonded there. Electrons now bonded there. That's what you get. This is actually a 3-membered ring. The chlorine is positive because you should be able to calculate a charge. Now, this species is not actually formed. And I say NAF. You're not going to see that in a textbook. That's my terminology. Because remember, we're under B. These reactions do not have a carbocation intermediate. This is not actually formed. How most books will show this is they'll show all this at the same time and they won't even show this. I think that's too complicated for beginning students. So I actually show this. I'll do the first step and then I'll back bond and I'll say here, but I'll have to say it's not actually formed. What's going on here is, and this is how most books will show it, as soon as the pi bond attacks the chlorine, the other chlorine is attacking here. So I'm going to attack the chlorine. Let's do it. You be the, can y'all be chlorine bonded together? Okay, here we go. No, you're not. They're chlorine. Here's a pi bond. Y'all are mad at each other. You pull and make her partial positive, and so I get attracted to her. Let's see. Okay. Now you have a long pair. Hold your long pair up. Okay. I'm gonna attack you. Make a bond to you. When I attack you, you have to pull your electron. Okay. So that one pulled its electrons away. Let's forget about it. As soon as I attack you, you bond here. All that happened at the same time. All this happens at the same time and we get here. Okay? This is not actually formed. I'm just showing this on the board. What I'm showing is, I'm showing first I bond to you. Okay. Now you back bond. See, we did it in two separate steps here. But actually, it's at the same time. As soon as I bond to you, you bond here. Boom, three-membered ring. This is not actually formed. This is the way I do it because of a variety of reasons. It helps reinforce some certain things. As long as you write NAF here, you're okay. If you don't write NAF, that means you don't know it's not actually formed. Okay, it back bonds. This is called a chloronium ion. It's a three-membered ring, positive charge chlorine. Yes, it is strained, but it's known to form. This is not final product, obviously. To get final product, the chloride, which has been watching because it didn't do this, it now comes in and bonds here. But it bonds not to a carbocation, but it bonds and kicks this off. So we do not attack a carbocation. This is called leaving group chemistry. Okay? In general, there's two ways to attack a carbon and make a new bond. You can attack a carbocation. Let's call this nucleophile. Boom. That would give a bond. Yeah. That's going to give nucleophile bonded there. The problem is, let's get rid of one of these carbons. Let's just make it secondary. Very standard. Nucleophile making a bond. Another way to get to this is to have some type of leaving group. Atom that can leave. And we can come in here and kick it off. That would give the same thing. Okay? Come in here and kick it off. That's what we're doing here. The nucleophile is coming in here and kicking off this chlorine. That's how the nucleophile, the chlorine, gets bonded here. There's no carbocation. Remember, these reactions don't involve a carbocation. Now again, if it attacked the carbocation, we would get that product, but that's not the mechanism. We'll say why later. Instead, it back bonds. This is the only intermediate. This attacks. Now, importantly, some terminology. This is called backside attack. Because when you attack an atom and kick off a leaving group, you attack backside, behind the leaving group, opposite side. So the leaving group bond is up, the nucleophile bond is down. That'll be important. Okay, another feature of this reaction. Why do we attack here and kick the chlorine off from there, as opposed to maybe attacking here and kicking the chlorine off from that carbon? It's because of this over here. Even though this chlorine is bonded to a carbon, we have dipole. Okay? Now it can also pull here. Which side is it going to pull more on? The answer is it's going to pull more on the side to leave positive on a carbon that can handle it. Which carbon can handle more positive charge? The one on the left. Why? That's the same as over here. Where are we going to leave cation at? Left or right? On the left. Why? Because it has donation. Well, that's the same thing here. This chlorine is going to pull more over here and leave partial positive more over here because of this donation. That is, this scenario is more likely. And this is illustrating sort of a partial bond where the chlorine is pulling. Ultimately, it attacks the same as if it would attack here. The difference is it's not attacking cation, it's attacking backside and kicking off the chlorine, and when you do that, there's your product. Some complex nature to it, yeah? I don't really think it's complex, it's just more than one thing to consider. There's four things to consider, but they're all pretty straightforward. Okay. So let's show products here. What do we have here? 1-butene. 1-butene. Is that cis or trans? Or neither? What if we reacted 1-butene with bromine? What's going to be the product? Well, in terms of regiochemistry, the product's pretty straightforward, right? We add a bromine to each carbon. Boom, boom, boom. Bromine here, bromine here. Bromine is added across the pi bond. It's actually pretty straightforward. Later on, we'll have to address stereochemistry. The stereochemistry here is quite limited. That is a chiral carbon. We can star that carbon there. But that's not chiral. Just for our notes, we can say that this is racemic. And that's actually pretty straightforward. There's nothing else to that. I imagine you were looking at that and saying, what am I missing? Well, that's a great question. You need to be looking at it all over the weekend and say, what am I missing? What else do I need to know here? Read the textbook chapter and say, well, maybe I don't need to know anything, or maybe I do. Okay, what is this here? ICl. This is actually an interhalogen. Similar, but it's two different atoms. Now this actually has a formal dipole. Which atom here is electrophilic? The iodine or the chlorine? Not the chlorine. Which way is the dipole? Chlorine's more electronegative, right? Iodine's partial plus, chlorine partial negative. It just comes from, it's an actual, there's no having to rationalize that. That's a polar molecule. The iodine's electrophilic. You know what electrophile means? Likes electrons. I mean, there's a difference between electrophilic and electronegative. Chlorine's more electronegative. That's why it's pulling. That leaves the iodine partial plus, and the partial plus iodine we call electrophilic. It's the thing the pi bond's going to attack. The pi bond's an electron. The electrons are going to be attracted to the partial plus. Okay? Ultimately, we're going to add an iodine to one carbon and a chlorine to the other. Just like here, we added bromine to one carbon, a bromine to the other. The question is, which carbon is the iodine going to be on? One position or the two position? Can you show that problem? Because here the two atoms are not the same. And in many of the reactions going forward, they will not be the same. So is the iodine, who says the iodine is going to be on the one carbon? Okay, who says it's going to be on the two carbon? Okay, 10 people voted. What come the others didn't vote? Okay, let's see where it's going to end up. Well, mechanism. Mechanism. What's the first step of the mechanism? Identifying the partial plus. These electrons attack partial plus. What happens to these electrons? They get kicked onto the chlorine. What does that give? Boom, boom, boom. So which carbon, where are we going to leave cation, right or left? On the left. So which carbon bonded to the iodine? On the right. Okay? Nothing new here. I mean, if we had reacted with H+, it would have been the same thing, except there would have been an H here. We didn't react with H+. We reacted not I+, but a partial plus I, and we had to kick off the leaving group. See, these electrons are pulled away and we go attack that iodine. Pull them away, attack the iodine, and this has to get kicked off. That iodine here plus what? Plus Cl minus? So the original question, where does the iodine end up? One position. It ain't going to move. Okay, what happens next? Does the chlorine attack here? No. Mechanistically, that would give you the product. The chlorine attack there, that would give you the product. That is indeed the product. The problem is, chlorine attacking there is not the mechanism. And it will not give you the correct stereochemistry if stereochemistry was important. What attacks the cation? Iodine back bonds. When it back bonds, what do you get? We get this iodine that's bonded back. It's a three-membered ring, two lone pairs, and that's a positive charge. And there's your, that's the so-called iodonium ion. Now, what do you want to say about this guy? Do you think it's actually formed? This guy's not actually formed. Because at the same time that this pi bond's attacking the iodine, what's the iodine electrons doing? See, they're back bonding at the same exact time. And most books will just show that. I just think that's a little bit too complex for you. So I don't show this arrow yet. I show it later. These reactions happen at the same exact time. This is not actually formed. By the way, what do you call it when reactions happen at the same exact time? Concerted. Okay? This is all concerted. This is not formed. This is your first intermediate. Now, how do we get final product? Now the chlorine comes in. Which carbon is it going to attack? We've got to attack and kick off the positive. Well, Which carbon has more partial plus? Right or left? This one, as we explained up there. Why? It's actually the same place as this. Now chlorine comes in, it actually comes in backside, it doesn't matter here. Kick off the leaving group. Now the chlorine's bonded here, and the iodide is only bonded there. When you kick this off, the iodine gets its third lone pair back. Chlorine only has 3 lone pairs because the other lone pair bonded to the carbon. And there's your product. Iodine's on carbon 1. You get that from knowing your mechanism, knowing the reactivity. You do not get the product with chlorine here and iodine here. You do not get this regioisomer. You only get this regioisomer. This reaction is thus regioselective. That's also racemic. We'll talk about that later. You can just have it in your notes. Question? People, make sure you speak loud, guys, because people over here want to hear the question.
I don't understand the last step. Like, why did the chlorine bind to that?
Minuses like positives.
So what's the bond between the iodine?
This bond here, these electrons broke away from that carbon and moved on to the iodine. It became the third lone pair. That lone pair used to be bonded here, but instead the chloride came in here and kicked it off. This is leaving group, like here. Nucleophile came in here and kicked off the leaving group. That's another way to get something else bonded to a carbon. Make a bond to carbon. As opposed to the nucleophile attacking a carbocation. See, there's nothing here to leave. But you can do a leaving, push something off. Does this iodine want to leave anyway? There's 2 reasons it wants to leave. First off, it's a strained 3-membered ring. It's like sitting here strained. Okay? If the chlorine comes in, I can't break this arm this way. Here we go. Here's the 3-membered ring. You be chlorine and attack here. Push me off. Now the 3-membered ring, all that ring strain is relieved. Also, now I'm no longer positive. So there's many reasons that this wants to leave. This is a minus, it's attracted to a plus. That's covered in physics, I think. Minus and plus is attracting. Yep. It's as simple as that. I mean, nucleophiles, electrophiles. We're making sigma bonds, which is going to be sort of going downhill. How many intermediates in this reaction? Only one, the iodonium. Chlorine does backside attack. We already mentioned why not F2 or I2. Okay, let's look at it. Okay, how do we know that this backside attack, the chloronium or iodonium, how do we know this mechanism is right? How do we know there's not actually a carbocation? Well, this tries to explain that. If you take this alkene and react it with chlorine, you're going to add a chlorine to each carbon, right? Interestingly, it's known you only get trans. The chlorines will only be trans. You do not get cis. Only trans. The reaction is thus stereoselective. in terms of diastereomers. Now you do get the enantiomer, which we'll be talking about later. The enantiomer is where all of your bonds are reversed. All of your wedged and dashes. The enantiomer would have dash there and bold there. Okay? The important thing is you only get trans, not cis. Now, if there was a carbocation involved, you should get cis. And the reason you don't is because there's not a carbocation involved. Let's look at this. If this attack, first off, this is symmetrical, so the leaving cation, either carbon is the same. Attack the chlorine, kick off the chlorine. That would give new bond to chlorine and a carbocation if we wanted to show it. Now that's tetrahedral, so we got a bold or a dash. You would get this. See, the pi bond is planar. If the chlorine is on the front, the electrons protect the chlorine and kick it off, and the bond to chlorine would be forward. But if the chlorine was on this side, the pi bond would go back, kick off the chlorine, and the new bond would be back. That's 50-50, okay, because you're going to attack from either side. So that's why you're going to get both of these, cation. Now, if it was truly a cation, chlorine just attacked. Let's just look at this structure. If chlorine just attacked, you should get both of these. There's no change here, bold, bold. But you should get both bold and dashed up here. Why would you get both up there if it attacked your cation? What's the hybridization and geometry of the carbocation? sp2, trigonal, planar. Planar is the important part. The cation is planar. Here's the planar cation. Now you can hold the plane like this, or you can hold the plane like this. I'll hold it like this. Okay? Or anywhere. I'm swimming around in your flask here. Okay? Now everything is like 50-50 because if the molecule is sitting here, that chloride is going to be on all around it, right? Okay? Here we go. Here's the cation, it's planar. Pretend the chlorine was over here, bond to here. Now the resulting bond is to the right, because the chlorine was on the right. But what if the chlorine was on the left? You make a bond. That bond is not on the right, it's on the left. You get both. You get a bond from the right and a bond from the left. When you attack the planar cation, you can attack from either the front, that would give this, or the back, that would give that. But this is cis and that's trans. And we said you only get what? You don't get cis. So, how do you explain that you don't get cis? The reason is, it ain't a cation. It's not a cation. Now, you can do the same scenario over there. Once we do more stereochemistry, you can see how all this is possible. But again, you don't get cis. You only get trans. It's just a duplication of it. This is just mirror image. The reason you get trans is because it's not a cation. Instead, what's going on? This attacks here, right? And maybe let's draw it up here. When that attacks there, what do you get? This chlorine was that bolded? Okay, that was bolded. Now it's bonded here, and that's bolded. That's a positive charge. Okay? I drew that there. That gives that. If that's bolded, why does that have to be bolded? If the chlorine's forward and it back bonds, the new bond's going to be forward. It can't back bond around back here. You get this. Now the other chlorine comes forward. And when it comes forward, it's going to attack here. How does it attack? This is backside. Backside. Anytime you attack and kick something off, it's backside. So if the chlorine is forward, where's backside? Here we go. If the chlorine's forward, backside is where? Back here. Let's do it here. If the chlorine is this way, where's backside? How are you going to attack? Yeah, you're going to come in over there. So come in over there. You kick me off. So that bond, if this is forward, that's forward. The new bond is back. Okay? Comes in backside, and what do you get? From there, you're going to get trans-only. The reason you get trans-only is because the chloride comes in backside. It does not attack a free cation. If you attack the cation, you would attack from either side. If you attack an atom and kick something off, you come in backside. And that's why you only get trans. Okay, guys, please do you need to please look ahead because we're going to keep up a good pace. We've introduced these reactions. We're going to keep up a good pace. For example, please be looking at these. Okay? This is halogen and water. It's called a halohydrin because that is Roman numeral 2. Okay? Halohydrin will be in the index of your textbook. You need to look it up and be working on predicting these. See some of you in lab this afternoon. We'll meet downstairs. And your lab will be turned in this afternoon. Have a good day, guys.
Oh yeah, do you want to?
Features twice on campaign and it literally says features twice on
Somebody closed
campaign.